So is there any particular reason why most of the students are still not able to attend this class? Does anybody know? Okay. Well, anyways, my job is to hold the class, and that's what I'm doing. Okay, so lecture 4, January 12th, 2020. Okay, so good morning, everybody. Excuse me. Last night, my daughter kept me up most of the night. That's what happens when you have kids. So in yesterday's lecture, we talked about how Lorentz transformations can be expressed in terms of matrices. And I introduced this matrix lambda, and I explained some of its properties. And then I told you that this matrix can be viewed as a Jacobian of a coordinate transformation between the two different frames of reference. And then talked about the invariance of the space-time interval between 2 points. And the fact that this space-time interval is invariant places a restriction on the form of the Lorentz transformation matrices. What is that restriction? That restriction is given by this expression. It basically says that when you have this Lorentz transformation, the metric remains unchanged under the effect of the Lorentz transformation. So again, I've given this to you as a homework problem, and I hope that at least some of you have attempted it. So let me, for those of you, some of you, many of you maybe might be feeling a little bit disoriented, perhaps. Maybe you're not used to thinking about these things in this geometric fashion. And so this expression might not make so much sense to you. So let me give you some motivation from a simpler case, which is the case of rotations in 3 dimensions. And what happens in 3-dimensional rotations, right? So again, we'll use so I hope everybody knows what the rotation matrix looks like, right? We have two vectors u and v, right, which are vectors in R3, and this R tilde is a rotation matrix. So it's an element of SO3. SO3 is the group of 3 by 3. This is the 3 by 3 orthogonal matrices, right? Matrices with unit determinant. Now, what does all of this mean, and why do we need all of this? So one aspect of this relationship is, so what does this tell us? This tells us that we take a vector and we perform a rotation on that vector, right? So there are two ways, first of all, two senses in which one can have a coordinate transformation. So this you should know. One is called active and passive. So again, if you are not familiar with these terms, what the active transformation means is that it is the vectors when you perform any kind of a transformation on some space, it is the vectors which transform. So you have some vector, it transforms into some other vector under the influence action of some symmetry transformation, where S is some symmetry transformation, whatever it is. It can be a symmetry transformation or it can also be a coordinate transformation, either way. Right? So as an example of coordinate transformations, you would, for instance, go from spherical coordinates to Cartesian coordinates and vice versa. What do we mean by passive transformations? Passive transformations are, so if you have any vector, again, now this vector can be written as, so okay, so let me mention that before talking about active. So if you have any vector, it can be written as the sum of these are some unit vectors which form a basis. Basis of our vector space. Our vector space is some vector space V, right? And any vector in our vector space can be written as in this way, right? I mean, this is one of the basic properties of vector spaces. And this E of I, these are the unit vectors. So as an example, if you talk about R3, you can have different basis vectors, right? You can have the Cartesian coordinates. What are the basis vectors? You have, let's say, x hat, y hat, and z hat, right? And then you would say that, for instance, any vector can be written as Rx, x hat, Ry, y hat. Here I'm using summation convention, so there is a sum over I, right? Rz, z hat, like this, right? X, y, z are some basis vectors. And what is the property of basis vectors? Basis vectors are, well, not always, but generally we want basis vectors to be normalized. We want them to have unit norm, and we want them to be orthogonal. That means if you take the dot product of any two basis vectors, this should give you 0. Right? So the first one is normalization. Again, this is not necessary. You can have a basis for your vector space, which is not normalized and which is not orthogonal. And this is this is orthogonality. Of course, you can have a non-orthogonal basis. So as an example, when we talk about crystals, so you can have a non-orthogonal basis, right? So for instance, if you can have two vectors like this, let's say this is E1 and this is E2, right? Now you can see these vectors are not orthogonal, right? E1 dot E2 is not equal to 0, but as long as these vectors are linearly independent, right? So any two vectors which don't have the same components in any given basis. So you can write any vector R in our space let's say this is a vector R, this is a vector sum R prime. You can write R as some combination of E1 and E2, right? R1, E1, R2, E2, right? And similarly, R prime would be R prime 1, E1, R prime 2, E2. Right. So this is just to give you one example. But generally, we take our basis to have this property. So what is an active coordinate transformation? An active coordinate transformation or an active transformation is one in which we say that it is the components change under the transformation. So as an example, you have your, again, I'll just work with 2 dimensions for simplicity. And we have some vector here R, and we say that there is some transformation that is applied to the whole vector space, right? So for any vector is transformed. So for example, there is a rotation, right? This is a rotation. Right? So what is happening now is that the basis vectors remain the same. Our basis vectors are X and Y. These are not changing, right? The components of R, when R becomes R prime, the components of R are changing, right? You can see that, right, from this picture. R has some components, R prime has some components. And it is those components which are changing. So right, the other way to look at the same picture okay, I got disconnected. Am I audible now?
Yes.
Yes, sir. Yes, sir.
Yes, sir.
Okay, so this is called a passive transformation. So this is also a rotation, but this is now passive, right? So in this picture, what is happening is, maybe I should make it slightly different. Something like X prime, and then our vector R remains the same, right? So now in this picture, what is happening? It is in the first case, what is happening? It is the components of the vector which are changing. So Ri goes to R prime I. And in the second case, what happens is that it is the basis vectors which are changing. So Ei goes to Ei prime. Ei are the basis vectors. So here X and Y. So these are the 2 senses in which transformations happen. One is an active transformation, the other is a passive transformation. So passive transformation, now for those of you who are familiar with in quantum mechanics, we have two different representations. One is called the Schrodinger representation, one is called the Heisenberg representation. So you can think of the Schrodinger, you can think of these active, in the Schrodinger representation, it is the quantum states which evolve with time. And in the Heisenberg representation, it is the operators
Sir,
which evolve with time. One second. So you can think of the Heisenberg representation like to be like the passive transformations and Schrodinger ones to be like the active. Yes.
sir, in the passive, the basis vectors are changing. Their magnitude is also changing.
It can change. I mean, it depends on the transformation, right? It depends on the transformation. So for instance, here I have shown an example of a rotation, right? But in general, the transformation doesn't have to be a rotation. It can be an arbitrary linear transformation, right? You can have translations, you can have rotations, you can have scale transformations, you can twist, you can shear, right? So you can have arbitrary linear transformations. So for instance, if you have like a rectangle in your plane, you can do many different transformations. You can squeeze it like this, right? It's being squeezed in one direction, expanded in another direction. This is called a shear. You can rotate it while keeping all the dimensions the same. No, sorry, this is not called a shear. I'm getting my words confused. This is a combination of scaling in the two different directions. So I'll just call this a scaling. And then you can have a shearing. A shearing, for instance, what it will do is it will take your square to something like this. So an arbitrary linear transformation will be some combination of all these three possibilities, right? So now this is what makes the difference. So what is special about rotations? In rotations, what is happening? When you have a rotation, which aspect of a vector remains unchanged? Whether you look at it in an active way or a passive way, it doesn't matter. So if you have a rotation, some property of a vector doesn't change. What property is that?
Magnitude.
Magnitude, right? Okay. So that means that magnitude means u square is equal to u dot u, right? How would I write this? When I say u dot u, what am I actually doing? I'm taking the transpose of u, the vector u is a column vector, right? And I write the transpose, so it becomes a row matrix. And this is the vector u, so I write that as a column matrix. Right? And then I take the matrix product of these two. That is what I mean when I calculate the dot product, right? So the correct way to write it is this. It is the product of the transpose of the vector with itself. So if you look at this equation and you take the transpose of both sides, what do you get? You get U transpose. What happens to the right hand side? If I have two matrices A, B, and I take the transpose of both of those, what do I get?
B transpose A transpose.
So if we take the transpose of this R and V, now these are both matrices, right? One is a column matrix and the other is a matrix, with both columns and rows. So this becomes V transpose R transpose like this, right? So then what happens to the length of this vector U? U is equal to U transpose U. So this becomes V transpose R transpose times R times V like this, right? And what is the requirement of rotations? The requirement is that the length of the vector should remain the same, right? That means that this quantity should be equal to V square under rotations, okay? So this is only possible if R transpose, right, multiplied by R is equal to what? The identity matrix. So which means that the transpose of R is equal to its inverse. And matrices which satisfy this property are called orthogonal matrices. The reason they are called orthogonal is because if you consider that, now I'm giving an example for a 3 by 3 matrix, but it's true for an arbitrary matrix, okay? If you consider some matrix R and you consider its transpose, right? Then what are you doing? You are taking, for instance, this row becomes this column in the transpose, right? And when you take the product of RT with R, what do? So let me make this RT and let me make this R. What are you doing? You are multiplying this row vector with this column vector, right? So if you want to get the component of R, so I have RT multiplied by R, this is a matrix, and I want to take the 2 component. The 2 component would be to take the second row multiplied by the second column, right? But in this case, these 2 columns, this row and this column, they are the same, right? Because of the property that this is the transpose. So if this is A, B, C, if these are some numbers A, B, C, then this is same number A, B, C, right? And what is this? This is A square plus B square plus C square. And I'm saying that this has to be equal to the identity. And this, what is this? 2 is one of the diagonal components. So this is equal to 1. Right? So the first property of an orthogonal matrix is that if I take any of its columns or rows, so if I take this column or I take this column, right? I take this one and take the dot product of that column vector with itself. What will I get? I will get 1. Right? The second thing is that Let me write these elements as DEF like this. Okay. What about the off-diagonal elements? Off-diagonal elements would be given, for example, by this row multiplied by this column. Right. So which element of the product would it be? This would be the third row. Sorry, the third row and the second column. So that would be DEF multiplied by ABC. What would this give me? This would give me AD BE plus CF. Right? This thing multiplied by this thing. But this is 0 because this is the identity. This has to be equal to the identity matrix. Okay. So if you take any two vectors, any two column vectors, and you take the dot product of two column vectors, that gives you 0. You can, the same thing applies to any of the rows. If you take any two rows, you take this row and you take this row and you take the dot product, you will get 0. So an orthogonal matrix can be written in this way. You can write it as a bunch of column vectors, V1, V2, like this, Bn, where each of the V's, right, V of I, let's say, this is a vector. It has components V11, V12, Vi1, Vi2, Vin, like this. And what is the property that if I take Vi dotted with Vi, it gives me 1, and Vi dotted with Vj, it is equal to 0, delta. So this is equal to 0 for I is not equal to j. That's why these are called orthogonal matrices. Okay, so this is something that once you understand, it makes the terminology clear. Right? So rotations, these matrices, they are orthogonal matrices. And I use this expression, I wrote down something SO3, right? So what is O? O means orthogonal. What is S? S means determinant 1, unit determinant. And 3 means 3 by 3. These are 3 by 3 matrices, right? So rotation matrices are 3 by 3. Any 3 by 3 orthogonal matrix with unit determinant, with unit determinant, meaning determinant is +1, is a rotation. Now, there is another way to write all of the same things. Now I'll write everything in this index notation. Okay. So if I have a vector u, I can write it, right? It has some components. I can write it as this u of I. And same thing, if I have some vector v, I can write. And again, for simplicity, I'm working with the spatial vectors for the time being. So when I ask what is the length squared of u, right? I write this u transpose times u. Another way to write it is as follows. I can write it as ui, which I can also write as delta ij, ui, uj. Okay. Same thing with v square. V square can be written as delta ij, vi, vj. Right? But this is only in Cartesian coordinates. Right? In Cartesian coordinates, you get delta ij. What if I have spherical coordinates? If I have spherical coordinates, then is my dot product involved this delta function, Kronecker delta? No, because if I have spherical coordinates, let's say u are u theta and u phi, these are my components, right? And then I ask what is u square? right? So u square is equal to u r square plus r square u theta square plus r square sine square theta u phi square. This is in spherical coordinates. Now, how this expression can also be written in the following way. I can write it as Gij ui uj, where Gij is a matrix which has the following elements. It is a diagonal matrix, but the components of this matrix are not all one. You get r square and r square sine theta. So if you look at vectors in spherical coordinates and you ask what is the length of a vector, you have to multiply it by this matrix Gij, right? So when I perform a rotation, what happens? The vector u is multiplied by some matrix R. So I can represent this as u of I goes to Rij uj. Okay. So what happens to the length of the vector? It goes to Gij ui uj. Okay, because remember, this matrix depends on your coordinates. If you're using Cartesian coordinates, this will be the canonical delta. But in some other coordinates, it can have a different expression. So what happens to this? How does this expression change? Under the rotation, this expression becomes, these quantities change, right? Ri becomes ui goes to this expression. Now, how should I write this u of I? The rotated one. I will write it like this. Rik uk. Right? So this is ui prime. This is the u of I after rotation. What about the j component? I'll write that as jl, u of l. This is uj prime. Okay, so what happens to u prime squared? The norm of the vector after the rotation can be written as follows. Rik Gij Rik Rjl uk ul. Okay, now if you compare this expression to what I had for the Lorentz transformation from the previous session, you look at this expression. So let me copy this and paste it here. What do you see? You see that these expressions are identical, right? This is the metric. Here it's Jij, here it's this eta, but they're both matrices and they both have the same function. They measure the length of a vector. Then you have the same, so again, you have this R over here, and so here R is a rotation, this lambda is a Lorentz transformation, but they are both some sort of linear transformations, right? And then finally we have our vectors. These are the vectors, right? So it's the same expression. and I require that this length of this vector should not be changed. So that means that this object has to be equal to what? Anybody?
Identity.
Huh?
GKL.
GK. Right? So this matrix, this metric, this is called the metric. This should be invariant under rotations. So in particular, if you are working with this thing, Cartesian coordinates, then you will get the result that your matrix R will be orthogonal. That orthogonality is not obvious if you are working with spherical coordinates. So what about these what can we say about these matrices? These matrices are also orthogonal matrices by exactly the same reasoning. These are orthogonal matrices. They also have unit determinant +1. So this lambda mu prime. These are orthogonal matrices. With determinant +1. Right? But when we say orthogonal, what do we mean? Remember that these are 4x4 matrices. Right? So for three-dimensional vectors or for Euclidean vectors, right? So these are all Euclidean vectors. And if you remember, Euclidean means that your distance function is given by the Pythagorean theorem. But we are working with Minkowski space, right? So our vectors are not Euclidean, they are Lorentzian vectors, right? So for Lorentzian vectors, orthogonality means that u dot v is what? Minus u dot v naught, u1 v1, u2 v2, u3 v3. And this has to be equal to 0 for any pair of vectors. So actually, no, I'm sorry. Yeah, in this case also orthogonality would mean the same thing. My bad, because you would get a minus sign from one lambda and minus from the other, and so you would get the same thing. This would again be delta ij. So where this is ui vj. So these are orthogonal matrices with unit determinant 1, and these matrices are put under the category of, they are called SO31. SO31 means special, unit determinant 1, orthogonal. The 3,1 means that when you take the inner product of any two vectors, you have to use the Minkowski metric. So this is the, let me give you the second exercise for homework 1.2. Show that So you have to show this explicitly. Okay. You can just copy my notes, or you can actually sit down and work out the derivation on your own. If you do that, that would obviously be would help you understand much better what's going on. Okay. All right. So I will stop here since you have another class at 11:15. Okay. Questions? Okay. I will stop the recording and the live streaming.